Hello everyone. Today I'll be talking a little bit about a distributed simulation and optimization system that can be applied for reconfigurable manufacturing systems. Simulation-based optimization allows several things such as final-based layout configurations, production planning, maintenance scheduling, and evaluation of what-if scenarios. The points in bold are the ones that are going to be present throughout this presentation. Previously, we developed a prescriptive system that recommends a sequence of throughput to be applied when a failure is detected. The sequence not only takes into consideration the weekly production target, since the main goal is to cover production losses due to machines downtime, but also the degradation of the remaining equipment. Here in this flowchart, we can see the general overview of the system. So here we have the manufacturing environment simulation that would be the real-world scenario, a simulation of a real-world scenario, and a failure is detected, which will trigger the optimization module. And the optimization module will generate several candidate solutions until the termination criteria is met. And each candidate solution will be evaluated through the simulation module, which is an image of the manufacturing environment simulation. Once this loop finishes, we suggest an optimized throughput sequence and the operator can choose to apply it or not. The solutions that we achieved with this system are good. However, it has a major drawback, which is the long processing times. And in this presentation, I would like to focus on how we decrease the processing times. However, before going into it, I'll briefly touch on the optimization module so it is easier to understand what we are really optimizing and how. We chose to use genetic algorithms since they offer good solutions to these kinds of problems, and each gene of the chromosome represents throughput of a machine at a certain day. For example, the first gene, it is the throughput of the machine 1 at day 1. And here in this slide, we have the fitness function that we use to evaluate each one of the solutions. And as you can see, we decided to formulate the problem as a minimization one. So we want the smallest fitness value as possible. And in this first term, we take into consideration the production. Here is the target, and here are the pieces produced under a certain sequence of throughputs. Next, we have the number of scheduled maintenances, and then the number of emergency maintenances. Here we have the number of maintenances in the next 3 days of the following week, and these last two terms are to prioritize solutions that offer more homogeneous sequences of throughput, since it's not realistic to change throughput all the time. And here we have the list of weights, and if you notice, the weight of scheduled maintenance is smaller than the one to emergency maintenances. And now that I briefly explained the optimization module, our goal is to make these systems suitable to real-world scenarios by reducing processing times and later integrating in the projects to support decision-making. So we are going to use a distributed approach, so several solutions can be simulated simultaneously, decreasing the processing time. And to do that, we are going to use Dinosaur since it allows distributed control systems and the later reuse of the function blocks. With Dinosaur, two pipelines were already developed to solve the traveling salesman problem, and here we are seeing the optimization pipeline. And if you notice, okay, here we have the optimizer that has inside a genetic algorithm and sends the solutions to the orchestrator. And the orchestrator is the function block that will distribute the solutions across the available simulators. And here in this slide, we can see the simulation pipeline where we receive the parameter from the orchestrator, it is simulated, and then it is evaluated through the fitness function, and it sends back the result to the orchestrator. To replicate the work that I talked about in the beginning, I'll reuse several of the function blocks that I showed you previously and change some of them. For example, here we can see the simulator. Let me turn on the laser. Okay, here, the simulator. And as you can see, I added several variables, so I can control the target and also some restrictions to the time domain, so I can control the working hours, the working days, and so on. And as I told you about, I need something to trigger the optimization module. So I added this event trigger optimization output that will activate when a failure is detected. And it will activate also this function block that will call the optimization module through MQTT. All the communications are done through MQTT. Also, the simulation module, the one here, to be able to evaluate and simulate the sequence throughputs, the candidate solutions, it needs to know the state of the machines, which pieces are being produced, where are certain pieces, and so on. So the simulator, when triggers the optimization, it will also send over MQTT a pickle file, so the simulation module has access to those variables. Here we have the optimization pipeline, and as you can see, we are subscribed to the topic call optimization, which will activate the optimizer. And the optimizer will generate a whole generation of 100 individuals, and that parameter can be set here in pop size. Also, if you want to change, for example, mutation rate or the number of generation, you do that here in these variables. Once we have the generation ready, the optimizer sends all the individuals to the orchestrator, and the orchestrator will distribute them among the available simulators. When the simulators are finished, they will send back the results by publishing them in the topic results. And as you can see, we are subscribed to that topic. When we receive the result, it is added to this queue. This queue is here because we are receiving several solutions very close to each other, and this approach guarantees that everything runs smoothly. And lastly, we have the simulation pipeline that is responsible to evaluate each individual. And as you can see, we are subscribed to the topic that has available the pickle file with the different states of the different variables, and also to the parameters sent through the orchestrator. And when we have these two variables, we can start the simulation. And when the simulation finishes, it sends over to this function block the results, so we can calculate the fitness value based on the fitness function that I showed you in the beginning. And when we have the fitness value, we need to put together the message that we are going to send back to the orchestrator. And to do that, we are going to use these two function blocks, and we send the simulation ID, so we know where it comes from, and also know that this simulator is ready to receive more parameters, the fitness value, obviously, and the parameter that is associated with this fitness value. And now that we have the system put together, we need to test it. And the scenario is this one. We have 9 machines operating during 5 working days. So the dashed lines correspond to the beginning of a new day. And the vertical red bands corresponds to that machine's downtime. And if we do not use any optimization tool, this will mean a decrease in production of 13.65%. So we started with 1 simulator, 2, 3, 4, and 8. And as you can see, when we add the second simulator, the processing time decreases in half. However, when we add, for example, the third simulator, it doesn't decrease 3 times. And as you notice here in this table, as we increase the number of simulators, the actual value deviates more from the theoretical value, because as we are adding simulators, we are also increasing the number of communications between the different components. And also, if we notice here the results given by the optimizer, between the different iterations, we had good results, and the differential never went beyond the margin that we consider acceptable, which was 1%. Here we have an example of one solution given by the optimizer, where we can see the different throughputs in the different machines throughout the different days. And also, if you notice in the machine MB3, the algorithm decided to decrease the throughput to -2, and this way The maintenance was delayed and coincided with the beginning of a maintenance shift, so before applying the optimization tool, this maintenance was an emergency one, and now it is a scheduled one. Our next steps will be testing the system with Raspberry Pis, where each Raspberry Pi will correspond to a simulator. Also, we will transform some of the function blocks into smaller ones, so we have more general function blocks and it will be easier to use them in the future. And also start the integration with a predictive maintenance tool, so the failure detection can be, for example, an output of a data-driven module. And that's all. Thank you.